Welcome, dear students. Welcome to the session of JEE Bytes. On behalf of Meritnation, I welcome everyone in the second session of Electromagnetic Induction of JEE Bytes. So we are here to help you all in your preparations of JEE. So good evening, Manoj, Preeti, Anjali, Janvi, Rosie, Wilson, everyone. Welcome to the session. So yes, as always, we will solve some of the questions of previous year JEE. So yes, let's begin now. Good evening, everyone. Okay, the first question. The variation of induced EMF, E, with respect to time in a coil, we have if a coil of and short bar magnet are moved such that the bar magnet is moved along the axis of the coil with a constant velocity. Okay, and which of the graph represents it in the best way? Okay, so how to find that? How to understand that? First of all, see, in the last class we had learned that EMF induced is given as minus d phi b by dt. Okay, the rate of change of flux. Negative sign we have. I hope you are able to recall that why we are having negative sign because of Lenz's law, right? So next thing, E is given by minus d phi by dt. So yes, as the magnet approaches the you say coil, the magnetic flux in the coil is increasing with time. Okay, it's increasing with the time. Okay, see, and you can see when the magnet is moving away, the magnetic flux is decreasing. Okay, so that's why we can say that the direction of EMF should actually reverse in both the cases. Okay, in both the cases it should reverse. So which of the following graph tells us whether EMF is getting reversed? Only the option B is telling us that the EMF is getting reversed. So that's why the correct answer is option B. So the next question. Next question. A metallic square loop ABCD is moving in its own plane with velocity v in a uniform magnetic field perpendicular to its plane as shown in the figure. Electric field is induced. Now, do you remember the electric field? If you recall, in the last class we had discussed that whenever a conductor, or we can say a metallic conductor, moves inside a magnetic field, whenever a conductor moves inside, or we can say when it cuts the magnetic field lines, as you all remember, there is force on electrons. Because electrons are being forced to move to one of the ends, this develops a potential difference. As well as we can say an electric field is developed in that, right? So electric field developed inside the conductor is a non-conservative type of electric field. It's a non-conservative type of electric field. Okay, why it's non-conservative? Because the net work done by this electric field in a closed loop will not be zero. It will be equal to the EMF induced. We're talking about work done per unit charge. Okay, so now let's see. Now, if you observe this ABCD square loop, and a square loop, if you observe, you can see that there is no change in magnetic flux. There's no change in magnetic flux. So that's why we can say that there is no induced EMF. But see, but if you observe one conductor, it's cutting the magnetic field. Okay. Overall, if you talk about a loop, in the loop, in the loop, yes, obviously the net magnetic field induced will be zero. But when we're talking about one conductor or one side of this square loop, you can see that it's cutting the magnetic field. So that's why electric field will be induced in both AD and BC. Okay. So, Sanil, dear, electrostatic field is conservative. Why? Because the net work done by electrostatic field in a closed loop is zero. But in this situation, the work done by E dot dl is in a closed loop will not be zero in the given situation. For a closed loop, the work done will not be zero. If you're talking about the charge, okay. Now, now students, we can understand that in both AD and BC, there will be an induced electric field. But you should understand that the electric field induced in both of them will be same. You know, it will be same. Okay, it will have same magnitude and same direction. That's why overall there is no charge flowing in this. Overall, there is no EMF induced for the loop if you talk about. Okay, let's move to the next question. Yes, a metallic rod of length L is tied to a string of length 2L and made to rotate with an angular speed omega on a horizontal table with one end of the string fixed. If there is a vertical magnetic field B in the region, the EMF induced across the ends of the rod is. We have to find the EMF induced in the ends of the rod. Okay. Before that, I would like to recall something. Before this, I would like to introduce the EMF induced inside a rotating conductor. That will actually help you out to solve this question very nicely. Suppose this is a metallic conductor, okay, and it is hinged here. It is hinged, okay, hinged here. So we can say one of the end is fixed and the other end, and now the complete rod is free to rotate like this. It's free to rotate like this. Okay. Now suppose there is a magnetic field and that directed into the plane of paper, right? Let us say there is a magnetic field that is directed into the plane of paper. Okay, let us say that the length of this conductor is small l, and assume that its angular velocity is omega. So how to find EMF induced in such a conductor? See, in the last session, we had discussed that when our conductor is moving inside a magnetic field, suppose there is a conductor that's moving in magnetic field, what happens in that? EMF is induced, and that EMF is given by BVL. Okay, BVL, where V is the velocity, L is the length, and B is the magnitude of magnetic field. Okay, students, now if you observe here, every part of this conductor is moving with different speed, with different velocity. So how to find the EMF induced. How to find that? In this given situation, we will apply this law to an element and integrate it for a complete length. Okay, let us say we consider some elemental length. Let us say the distance of the element from the hinge is x. This is x, and this length is dx. Length of the element is dx, we have assumed. Okay, so can we calculate the velocity of this? Can we calculate the velocity of the element? If the complete rod is having omega as the angular velocity, so for every part we can have the same angular velocity. Okay, now we know that velocity, the linear velocity is given by omega times r, where r is a distance from the center or the axis. So here, if you talk about the velocity for the given element, its velocity will be equal to omega times x. Omega times x. And what's the direction for that? Yeah, the direction is vertically upwards. If you say it's horizontal, it's vertically upward like this. So this is the direction of velocity omega x. Okay, so now the EMF induced across this, element will be given by b omega x and dx. Okay, so how to find for the complete length? Just integrate that. When you integrate, you'll get the EMF induced for the complete length. So now just you have to ponder, you have to think it over how x is varying. X is what? X is a distance of the element from the end. X is the distance of the element from the end. Okay, and how can we vary x so that we can cover the complete length? See, x can be made to be 0, minimum to be 0, and maximum to be L. So from 0 to L, we can vary the x. So next thing we have to do is to integrate. So yes, B is constant quantity, omega is a constant quantity, and now x dx 0 to L. In this situation, it will be equal to b omega x square by 2, and the limits are 0 to L, and that is equal to b omega L square divided by 2. This is the EMF induced in a rotating conductor. Okay, EMF induced in a rotating conductor. In a conductor rotating in a magnetic field. Okay, now you can easily solve that question. If you have seen this derivation, you can easily solve that question. Now let's see the question. A metallic rod of length L is tied to a string of length 2L and made to rotate with angular speed omega on a horizontal table. With one end of the string, if there is a vertical magnetic field in the region, the EMF induced across the ends of the rod is. So what we have to find? We have to find the EMF induced, like in the previous case. So how to do that? Same question. But in this question, What's different? The limits are different. The limits will be different. How to do that? Same way, if you want, you can apply that direct formula, or if you want, you can integrate also. So suppose this is the thread, this is a thread, and yes, and this is the rod, and the length of the rod is L. Length of the rod is L, and 2L is the length of the thread. This is 2L, and this is L. Starting from, now see, if you start, if you take element from this point, if you take, because the conductor and the thread are moving, or they're rotating about point O. So omega, yes. So again, take the element like this, and let us say this time that this distance is x, and the length of the element is dx, and assume that, yes, the what's the velocity of this? Yes, we can easily say that velocity omega x. Velocity will be omega x. So same way, the dE, that means the elemental, or sorry, the EMF induced element will be given by simply BVL. So omega x times dx, because length is dx. So next thing, integrate E from, so you can say, yeah, this is the value of E. So B omega integration of x dx. Now, just check what can be the minimum value of x and what can be the maximum value of x. The minimum value of x can be 2L, and the maximum value of the L can be 3L. So 2L to 3L. So simply integrate this. So what do you get? You get simply B omega times x square by 2 with the limits 2L to 3L. Put the limits here. So what do you get? You get E is equal to B omega times 9L square minus 4L square. And finally, what value you get? You get simply E to be B omega times 5B omega L square by 2. This is the final answer to the given question. So yes, the correct answer in this question is D. So dear students, if you observe what can be the direction or polarity of this EMF induced, you should understand that the EMF induced is such that it behaves like a battery like this. Okay, the hinge point, the hinged point is always at higher potential. The hinged point is always at higher potential. And the outer point is at lower potential. So you have to understand this. Okay, so that's all about the EMF induced in a rotating conductor. Now let us move forward to the next question. So two circular coils can be arranged in any of the three situations shown in the figure. Their mutual inductance will be, what we have to find? We have to find the mutual inductance. Okay, or we have to tell in which situation the mutual inductance will be maximum. So how to do that? If you recall, if you recall, you suppose we have two coils. Okay, let us say this coil is connected to some power source, so that, and the power source is changing. Okay, or you can say the power source has variable EMF. Okay, variable EMF. So in that situation, we can see that I, a current flowing in this coil will be variable. And because of variable EMF, variable current will have variable flux, right? Will have variable flux. And the flux induced will also be variable. And that variable flux produces EMF in the other coil. If it's a closed coil, in that situation, a current will flow in that, such that the current induced will be in such a direction that it will oppose its cause. It will oppose its cause. Okay, if you remember, if L1 and L2 are if L1 and L2 are the self inductances of the coils, the mutual inductance is given by this formula, K times under root of L1 L2, where K is the coupling factor. Okay, K is a coupling factor, and it tells us what tells us? It tells us how the flux is being, related with the coils. Okay, so it depends upon this K depends upon, or we can say M also depends upon the flux linkage between the coils. Okay, it depends upon how the flux is being linked between the coils. So if you observe the three figures, or three, you say, configurations of the coils, you can see that in A, there's maximum linkage of the flux, whereas in the second one there's a minimum linkage of flux, and C also, in the case C also, will have very less linkage of flux, because most of the field lines will not pass through the bigger coil, if the current is flowing the lower coil or smaller coil. So that's why we can say that the flux linkage is maximum for A. And if L1 and L2 are the self-inductance of the two coils, if L1 is the self-inductance of the first coil, L2 is the self-inductance of the second coil, so M is given as K times root L1, L2. So K is a factor that is dependent upon the flux linkage. So in the case A, is the maximum flux linkage. So that's why the value of K is maximum for A. That's why the correct answer for the given question is A. So I hope all of you are able to understand. You can see the recording of later on also. This part you can just visit again. It's very important. Just revise it again once. Okay, and try some more questions like this. It's important for your preparations. So thank you so much, students. I hope you learned a lot today. So thank you so much. To know how we can help you in your preparations, you can see the given link. You can see this link, and the same link is mentioned in our description box. So all the very best. Thank you so much.